Barbara?
I've got it. Should I start to record
No,
now?
yes, start to record. Tell me.
All right.
You're recording?
I'm recording.
Okay, welcome. Welcome very much to the ACAP, Association of Access Cable Producers, where we're honored to have a real pioneer in my way of thinking, that being Carter Emmart. His title is the Director of Astrovisualization, mouthful, at the American Museum of Natural History. And it's one of the largest planetariums in the world. And the planetarium environment is the largest video display screen in the world, collectively. There are various dimensions and so forth, and I think Carter can talk about the dynamics. As I understand, there's an array of 5 going around on the circular and a keystone, and it's all integrated as one system seamlessly, so you have a hemispheric projection of image. The improvements in the image available, also the sound, I guess, is getting better and better, but the planetarium makes IMAX look like a Cineplex and a television screen like a little slit in the wall, as opposed to viewing the world the way we walk through it, multisensorially. And it's a huge thing, and from what I understand, he can talk about it. It's getting now into the realm of where it's going to become available as an element of architecture in the world. As the costs come down, it'll actually be able to come down to a unit in even a residential, to have a den, as you know, a living room, and a planetarium to display multimedia presentation of access to the knowledge of the world in a way that is coming. Intelligent television is coming. The best way to project it are the planetariums, and he's on the leading edge of that, and he's in touch with the community of people that form that camaraderie around that issue. So, without further ado, he's going to talk for a little bit, answer a couple questions, then we'll turn off the lights, and he's going to run a slideshow of images that he has. But without further ado, let's welcome Carter Emmart, Director of Astrovisualization, and take it away, Carter. Thank you.
Well, thank you, Harold, for providing this opportunity, and thank you all for coming tonight to see this presentation. It's a great honor to be working in the field that I am. As a child, I grew up going to the Hayden Planetarium. My mom used to drive me in from New Jersey, where I grew up, and to the Hayden Planetarium on the weekends. And I wanted to pursue astrophysics as a career. I came from a family of artists, so I ended up in the field of data visualization. This brought me to essentially the field that I'm in now, which was to visualize astronomy at the turn of the millennium, when the planetarium, the Hayden Planetarium, was rebuilding itself. So really, we just passed our 10th anniversary in October. We actually opened our doors in, I believe, February of 2000, when we reopened the Hayden Planetarium, now housed within the Rose Center and space of the American Museum of Natural History. And the concept was to go from the tradition of the planetarium. The planetarium had been devised in a modern sense in the 1920s by the Zeiss company in Germany. And that was to create an optical mechanical star projecting device in the middle of a dome. And so it would throw the stars out on the dome and recreate the sky. And so this really was the way of planetariums up until the turn of the millennium. With the advent of full dome video, such as Harold described, where we make up the resolution, this IMAX scale resolution, if you will, with video. The video allowed us 2 ways to go in a manner. For our main productions that we create and that we produce, put out there for the public, we make a movie. A movie allows us the ultimate control and allows us to have a star narrator, such as we've had, and allows us to distribute around the world. And what we do in these productions for these movies is to data visualize the science. In this case, be able to create these three-dimensional data sets of essentially what we observe around us as a map, or the real map of three-dimensionality of what we now know, star distances, where planets are, if we wanted to fly past Earth or Moon or something like this, in the same way that we do Hollywood techniques and movies like Star Wars or Star Trek, flying around in a sort of 3D universe. But the difference in being from a museum such as the American Museum is one where we're concerned with actually providing and bringing to you the actual science. And so there are these two modes. There's one that's movie, and the other is interaction. And with interaction, you can essentially control the view of what you're seeing. And that we started, when we started off the project, while we were still building the Rose Center, we were investigating this interactivity, mainly because the storage of a movie at the resolution we were talking about, like IMAX resolution, have that digitally stored required a lot of storage capacity. And storage capacity, just over a decade ago, was extremely expensive. And the story of the last 10 years is that technology, that storage has become cheaper and cheaper and cheaper. So that storing a movie is really no problem. But that interactivity was, the generation of the image in real time, as we say, was a means toward possibly delivering the show, a scripted show, but delivering you the show. A show that was, again, based in science. And what I mean by that is that we had to consider how we were going to go from essentially a projection in the planetarium world of stars, or the two-dimensional looking sky. We know the sky has depth. We know that the stars are the different distances, and the planets and galaxies beyond, and all this. But if we were to show this on the planetarium dome, if you sat at Earth, of course, everything just looks like sky. But if we move away from Earth, if we go to Alpha Centauri, the stars are going to change in their perspective of what they look like. And indeed, if we move beyond our galaxy, we would see all the stars coalesce into the glow of the galaxy. We would see the other galaxies. And we'd be able to move through this database. What really happened in recent times is that we have been able to, mainly through computational science and many observations, is the creation of new types of telescopes, new surveys that are linked with taking digital imagery and being able to analyze that imagery on a massive scale so that we can decipher tremendous amounts of data for stellar distances, for galaxy distances, that for the first time we were able to have this three-dimensional map of the entire cosmos. So our job became one to do productions, make movies of this map of the cosmos, as well as be able to sort of fly through it in real time, interactively. And so we developed
Jackson.
I see I have a fan.
Yes.
Yeah, hello, we'll bring you in and then open the elevator and
So the notion really became one of being able to provide a movie of sort of fundamental topics of astronomy and astrophysics, which is what we do with our main shows. We've done 4 shows in the 10 years we've been open. We did Passport to the Universe, which is about the scale of the universe. Search for Life, Are We Alone? That was our second show that addressed what we know about life in the universe, or the conditions for life. We know of only one planet of life here, us. But we are beginning to find planets, or we've now found about 500 planets around other stars, which is amazing. And that's just very close to us, as you're about to see. I'll show you. You know, if planets are common, then the conditions for life as we know it, these sort of habitable zones where we might find liquid water on other worlds, even in some cases within our solar system, mainly to have an atmosphere with water, liquid water on its surface, and like Earth, or Earth-like planets. We don't have any Earth-like planets in our solar system other than Earth. Mars is most Earth-like, but it's cold and its atmosphere is very thin. In the past, it seemed to be like Earth. So, looking for life is a driver behind the space program. Our third program was called Cosmic Collisions, our third movie. So it looked at the process of dynamics and throughout what we know of astronomy, throughout the universe. Galaxies collide, stars collide, planetesimals collide, planets still sweep up debris. The impact of that Chicxulub, 65 million years ago, the impact just off of the Yucatan Peninsula that killed off the dinosaurs. These sorts of things we looked at, cosmic collisions. And the most recent movie that we created was called Journey to the Stars, where we actually look at what the sun is, what the stars are, and so we investigate that. At the same time, this interactivity that I mentioned that we began with as kind of an insurance to see if we could make our show work at a time where we thought storage might be too difficult to actually store a full movie, that we began to see that capability to fly through, as I say, move about through this 3D map of the stars and the universe was a tremendous way of teaching our location in the universe, that it allowed a pace, and with a group of people like yourselves that we would sometimes bring in after hours, and we would linger in the data set and move through it. It's a different type of experience than just sitting down and watching a movie. And this ability to sort of understand that you're in the data set is rather profound, because you realize that you really am in a big three-dimensional arena, that this is real stuff.
When you say move through, is it you that does the moving,
yes,
or the individual?
Yes, it is that we have a pilot, himself in this case, and we move through it. And you need not only just a pilot.
So the audience follows you.
The audience will we all go together, and so I'm the sort of tour guide, if you will, in that case. And
yeah, you might mention you're going to have a show coming up. Yeah, we're going to project it.
Right, and so we'll show that. So that you have these modes. One is the movie, which we can distribute, and but also this interaction, which is a different experience, because you realize fundamentally that you're in this, because choices are made. You go left or you go right. You're seeing this interaction, and somebody asks a question, we stop, we linger, and look. So it's a different way of looking at it. And this data set that we put together has to be maintained, because we're finding new exoplanets all the time. Galaxy surveys, just in the last 10 years, for example, when we started out, the galaxies that we knew distances to beyond the Milky Way were just some few thousand when we started out about 12 years ago. Add to that now about 2 million galaxies that have come in sort of 3 or 4 significant surveys.
2 million galaxies?
Yeah, and this is a testament to the ability for computing to plan new telescopes and to carry out the surveys and process the data, and then finally to visualize that data and put it into a system like this where we can see it, but continuously we can go from, say, the Earth all the way out to see all those galaxies from a distance, a perspective, to roll it around to sort of see their spatial arrangement around us. And by the way, these surveys are incomplete as well. because they're not, we don't have the entire sky surveyed yet. So you can see what's missing and what needs. And I just mentioned as well is that it's one thing to move through these data sets, but it's another thing to sort of move through it with meaning. You need someone to be able to tell you, oh, well, this star is a star, and here is this, and here is that. You need something to put together the various pieces.
He's going to mic you, that's all. So he's doing. Let me ask a question while he's doing that. The Rose Planetarium is called the Rose Planet of Earth and Space, and these images of the universe are one thing, but you can also get down on into the experiences on Earth itself. And then could you make a distinction between the way the planetarium is done technically, you've got 5 arrays, and the world of television, high definition, and so forth, and how are they going to come together?
Well, what we do is we actually create the image on the dome by a mosaic of 6 images. We have video projectors that project, so the technology of the dome projection is one where we have 6 projectors. They each project across the dome. So there's a panorama of 5, and then there's a high angle one that's keystoned, as Harold mentioned, that to fill up the hole, the pentagonal hole above the 5 arrayed projectors. That's not the only way one can project into a dome. There are systems that have very high resolution projectors where they're just 2 projectors and they cross project like this, and there's one seam of a border between the 2. There's also systems that have a fisheye projector, and for smaller portable inflatable projectors they have systems like this where you have just a fisheye. Now I should also mention that in this interactivity comes the ability for more than one site to be online with other sites. Just as video games now can be shared anywhere around the world. You could be playing World of Warcraft, you could be fighting somebody and they could be in China, as far as you know. They could be anywhere in the world, and they're all playing the same game. In the same manner that different planetariums that have this software, which will be running here, we go online together, and the software is running the database that's sitting on the computer. It's not running it off the internet, but what the internet provides is the simple manner of telling the other planetarium where the camera or where the viewpoint is, and maybe the aiming. And that's about 6 numbers. You say X, Y, Z of where I am, and roll X, roll Y. You get basically an aiming instruction in 3 space and a position in 3 space. What this means is that we can go online with other planetariums and fly, maneuver through this real data map together. And so I was going to have, if I was online tonight, I was going to have Joel Halverson from the Minnesota, from the Minneapolis Planetarium. They're actually in the midst of rebuilding their planetarium. They haven't rebuilt it yet. So Joel, as program director, received an inflatable planetarium, which they take around to the schools in Minnesota, and they have a fisheye projector, the same database, the same software. Excuse me. And he's just past having his, he's had 100,000 students in the last few years. They've just had their 100,000th student actually see this, so they take it around. We also presented in October of last year, excuse me, October of 2009, we had an inflatable planetarium, thank you very much, on the south lawn of the White House for the first presidential star party. And so Barack Obama hosted this, and we went down and we presented on the South Lawn in this inflatable planetarium, and we had 3 planetariums in Minnesota actually online with us together, and we had questions coming from them from the tour of the universe, which I was guiding, and a colleague of mine was actually flying.
Dancing with the Stars?
Buzz Aldrin was there that evening. I didn't ask him about his appearance on Dancing with the
But
Stars.
Carter, if you're projecting at 5, 6, is there
Well-
6 different cameras were recording that were integrated?
Well,
properly?
that's
Now, how do
okay.
they mesh
Okay.
with video?
Okay.
or audio?
The video projection projects, in the case of a large dome, multiple video projections, and as I said, you could also project it as a fisheye. That's the technology. Each projector is projecting essentially one view. So it would be 1/6 of a hemisphere. And that's coordinated, but that's the technology of the display. And I should mention that when we actually act as a pilot for presentation in the dome, we don't look at the dome, we look at a flat screen. Tonight here I have my my laptop, and on the laptop that I will now project for you is that, and what you'll see projected, of course, is a rectangular video projection, is just one portion of what would be a dome if one was to stitch together the surround visual. What I would like to emphasize is, whereas the dome is a wonderful and perhaps unique type of environment, as Harold, you gave an excellent description in the introduction, that it provides you with the way we see the world. I look out and I see a sort of hemispherical view in front of me. Excuse me, I have a cold. That the single screen, wide field view is the way that we are used to now with media seeing the world. Television, movies, and the internet. So that this ability to use just, say, a rectangular screen to understand and see this database is something that does not require the dome. And it gets into the last point I want to make, which is that whereas we can go from dome to dome, and also I mentioned that we drive it with a flat screen, is that we may be presenting in domes, driving from a flat screen, but we can share that flat screen or that control. Okay, thank you. We can share that. Thank you.
Get ready.
Thank you very much. We can share that. We can share that with classrooms around the world. I've taken 2 machines to a high school in Siem Reap, Cambodia, which is the gateway to Angkor Wat. And I took it to that particular location because when I visited there, I realized that Angkor Wat was a 1,000-year-old model of the universe. And so 4 months later, I was back with a machine which I felt that that they needed it more than I did, and so I took this machine there. And the Cambodians have actually controlled the Hayden Planetarium from their high school there. Add to this the first homemade sub-Saharan digital planetarium in Africa, in Accra, Ghana. Dr. Jacob Ashang has, in his retirement funds, put together a 10-meter dome. And Dave Weinrich, who is the president of the International Planetarium Society, had worked for Peace Corps. And he had worked out a donation of a fisheye projection system. And when they opened last January, which was, I'm sorry, this 2009, so it's just over a year ago, 2 years ago, sorry, that this was the International Year of Astronomy. And that represents 400 years after Galileo had discovered the moons of Jupiter. And so for that opening ceremony, we actually presented from New York the Atlas of the Universe, which you'll see here tonight, to Accra, Ghana. And also to Medellin, Colombia, which was a former drug war zone. And in the last decade, it's been completely turned around. And a former slum is now their science center. And I had the great honor of presenting to them remotely. They then brought me down there, and we presented from the science center to 5 of what will be 9 libraries that have been built straight in the center of the ghettos, up in the favela, or on the sides of the hills. And a tremendous thing is happening there, where they've turned the drug wars around, and they've put these libraries in their community centers. There's also places for child daycare and so on. Yes?
One thing about, it's the rose, earth, and you're talking about, you know, the stars and the universe, and that's one thing. NASA databases, Earth, travelogues, tigers and lions and windows, you know, have a thing that is earthbound, and
well,
showing things, or showing feature movies
yeah.
or something like that.
Well,
in surround. I mean,
well,
the
let's,
Earth.
okay, this is a really good point. We're a planetarium, and so our focus has been to look out.
Yeah.
Now, go beyond the sky into space.
Yeah, yeah.
But when we first had the interactivity, bringing people in, say, late at night and the weekends, was that we didn't really have an Earth to come back to. We went away from Earth, and we had a solar system depiction, but we couldn't see the Earth. And we realized this, but that notion that we want to see the Earth, we want to see the Earth in space, we did just what the Apollo program did, was we threw all the technology of getting at the moon. In this case, we threw all the technology of getting out into that deep space. But the most meaningful legacy of the Apollo mission was the picture of us in space. It wasn't the lifeless moon, it was the life-full Earth.
Yes, right.
And so that now, coming back and seeing our place in space is perhaps the most important aspect of this, is that understanding the cosmos and understanding the stories of astrophysics and all that, that's great. That's our cosmogenesis, and understanding that our home really is space. That, as Buckminster Fuller said, that his reaction to looking at the Earth rise above the moon was its spaceship Earth.
Yeah.
That realization, that juxtaposition, that new realization that the Earth really, that is us. We all are already in space. We don't need to go in a rocket into space. We're already in space. In fact, in 4 hours, we cover the distance. As we go around the sun, we cover the distance from the Earth to the moon in 4 hours. And that distance took about 2 to 3 days for the Apollo astronauts to get there. And we're traveling much faster than that as the sun carries us with it around the galaxy. We are in space. It's something we know, but it's another thing to kind of realize. And that this realization brings us closer to the things that really matter. The only planet that is our survival, the only planet which is our home. That we need to manage ourselves better as a species, to see the Earth as it truly is, to map in the satellite photos and see our planet, and to also see what the astronauts have told us they see, which is we don't see the borders, we see how thin the atmosphere is. And that from that perspective, all our petty little rivalries and everything else that we run around screaming about, you don't see the people, you can see the cities and all this, but it just seems absurd from that perspective.
If you want,
So,
with Spencer Wells, to have a journey on the Serengeti Plain, and you're surrounded around with leopards and elephants and things like that on the Earth, do you have to have 5 cameras going in different directions?
Well,
or can we, and can
you
you
would-
get down to feature films, The Godfather, in surround sound?
well, you can film with a fisheye lens, and you can film. Now, this was also a company called OmniMax was created to do that, in the early 70s, at the same time IMAX was coming out. IMAX bought them, and it became IMAX Dome. What was lost in that was the ability to really make productions in fisheye. IMAX bought out OmniMax as a means to just have more screens. OmniMax was to film with a fisheye lens for surround. IMAX was filming with about a 90-degree field of view, and they would project it into a dome and stretch it out so there's distortion. But it was not true immersive filmmaking. What we have now is the capability to do immersive filmmaking. So that is here now, in a way like we haven't had before.
Okay, well, I don't know, there's all you're going to show us a slideshow, right?
I'm going to not show, no, not a slideshow. I'm going to take you through the universe interactively in the program.
Well, I would suggest if it's all, anybody have any burning questions, I suggest we turn off the lights, and then you can come over, and if you can get the dog off your chair,
Yeah.
He's probably cooperating. And then could we also turn off the lights, like over there?
Yes, please.
And let him, all right. Jack,
Thank you.
I'll bring
Great.
this.
Okay.
Get down. Good dog.
Now ask him up there.
Move the chair.
No, he doesn't want it. Okay, and lights, I'll get them over here.
I get water.
No, don't start getting up.
I just want water.
Okay.
I have one question, Carl.
Yeah.
We gotta turn off the lights, and then you can, Carter, can just start talking.
Okay.
And we'll put the camera on it, and let's do that.
We got one question while they're waiting.
Okay, go ahead.
From all of this technology and all of these experiences that you're putting together here,
Oh, thank you.
has any
Great.
original
Thanks.
astrophysical or other kinds of research or discoveries taken place besides just entertainment and education? As a result.
As a result of
Of creating all this technology and going through creating all these experiences, of projecting into the universe, of looking here and there in this artificial way, have you discovered anything essential in astronomy or physics or
well,
science?
the sciences are finding the fundamental discoveries. We are just being able to present them in ways
Has
unlike
this
before.
technique added to the ability of scientists to find things?
In visualization, absolutely.
Okay.
Visualization techniques allow us to see the invisible, and that's been the goal, is to see things that, in other words, taking the information and visualizing it, creating maps effectively of what was not possible before computationally.
So
and
it's
so
more than education and entertainment.
It is, and in this case, this is data visualization in the service of public education. Informal public education, in the same grand tradition of natural history museums, similar to our displays of dioramas and so forth, of looking at the world. The goal of this is to take you there. The goal of this is to be able to present these perspectives in a way that were never available before. For example, if I'm just to come in close, say, here to, we're coming into the island of Sumatra, we see Jakarta, so we're over Indonesia, and coming up over the Malaysian Peninsula, and coming up to a favorite part of the world for me now, Southeast Asia. My girlfriend is there, she's Thai, and Cambodia, where I've taken the machines. But the ability to do this, I am taking a map from satellite views, and we're now sort of moving slowly over this slow orbit, but I'll use the cursor to point out the atmosphere, showing the way the atmosphere actually presents itself on Earth. This is an effect of graphics, but it's accurate in scale. The atmosphere is only 20 miles thick, or 30 kilometers. And this is from space. This is how people react to why the astronauts react to in astonishment, almost in horror, at how thin the atmosphere actually appears. Now, if you will, I'm going to just reduce this down for a couple reasons. One is I can actually get a read of my distance. Now, I want to actually bring us down closer to Earth, how close the space station flies, which is only 400 kilometers. So, and in so doing, I'm going to keep us tipped over to the view that we've been having. But okay, I'm going to come up just about
The space station is
there.
geostationary?
No, the space station is in what we call low Earth orbit. And it's only about 400 kilometers off the surface. So I'm adjusting the number here that we see. Now, I've also got the clouds off, but I'm going to I want to bring up a layer control here and bring us back to full screen. And I'm going to get rid of some of these things. And I'm going to point out, this is the Brahmaputra River coming out of, this is the Himalayas here. And so we have India and Bhutan, and this is Myanmar here. And the Brahmaputra comes down, flows into the Ganges, into Bangladesh.
Is that what feeds the Ganges from the glacier?
What feeds the Ganges and the Brahmaputra are the glaciers of the high Himalaya. And we can see Mount Everest right here, in fact. And then the Tibetan plateau beyond. And if we now tip back over, we can now see how it's green on the lower side because of the Indian monsoon coming in here. And then the high altitude Tibetan tundra in brown. And the Valley of Lhasa is right here. If I come down closer, we should be able to see that. Now, some of you may have seen the piece that we did that's on YouTube. It's called The Known Universe. And that was a piece where we used this very software to create it. But here you are seeing it interactively. So this is the Valley of Lhasa.
Resolution staying constant as you zoom in?
No, it's not. The resolution's sort of reaching limits right now, so I'm not coming in any closer. I could try to bring in a Landsat mosaic, and I'm not sure if I actually have the resolution. This would have to be resolution that was cached or on my disk, and I think in this case I do not have it. If I was online, I could get a higher resolution. I'd have to wait for it, but since this is why I wasn't using it, because we seem to see low res. But this is, in fact, high resolution that's on the disk. Now, what I'd like to do is actually add in a view of the Earth of a particular day, and I can explain the difference between these two images. So let me just come up here and sort of freeze for a moment. This is an image of the Earth from September 8th of 2008, and where this image is gathered by a NASA satellite called Terra, and it takes a full color image of the Earth down to 1/4 of a kilometer in resolution. And then we see this image, which we were looking at. So again, if I page back and forth, we could see the difference. Or if I just put this, I could sort of do this with transparency back and forth. Now here you can see there's already been snows and things and so forth. And, but this is an image for July, and it's a monthly average. So for July, what they've done is they have filtered the daily image to get all the clouds out, or as many of the clouds out of the way as possible. And this is because they have observed Julys over the past 12 years, because this was, or 11 years. It was launched in 99, I guess. So I guess about 12 years. So here I can just play with the sort of layering transparency of one current daily image over a monthly average. And that's what you can do with the image processing that NASA provides. And so just see how, if we look here at these lakes of the Tibetan Plateau, you can see that they're in the proper location. Okay. And farther north, we have the Taklamakan Desert of western China. And this is actually a quite beautiful area. So what I would like to do right now is I'm going to increase the time. There, so we can kind of see some of the details here. And then I will begin what I call a flight. Okay. Here with the image such as we're seeing, we're actually seeing the Earth very much like the astronauts would see it from space. And so what I want to do is pull around so that we can see, say, the Taklamakan Desert, which is quite beautiful. Oh, back here we can see this is Taurus the Bull, there's the Pleiades. So now I'll just begin moving, and we can essentially fly anywhere. Now, okay, say I want to come over to the mountains to the north in Uyghur country. And I can come lower if I'd like. But we can see the shadows of the clouds. And we begin out here in western China, that the beauty of the landscape is, you know, it's intense, and but you don't always know where you are, and you don't have a heads-up display telling you exactly what country you're over. The astronauts all talk about sort of falling in love with the Earth, looking down, and that they all relate to it as the Earth, because up there, it's, you know, it's who's to say, unless you're a geography expert, where exactly you are, and that the borders are just not obvious. So now let me just pull away from our planet so that we see it in greater relationship. And once again, I'm just going to do the following so that we, okay, there. Yeah. Now if I pull back to about here, I can turn on some satellites for us. And I'm going to turn on the 100 brightest satellites for the moment. And I'm going to start to run time.
Wow.
And you begin to see, that's just the 100 brightest satellites.
How many satellites are there?
Well, let's add in some others.
Oh my God.
So let's turn on navigation satellites. Oh, hold on, let me turn on all of them. Well, there are thousands.
Thousands?
Oh, yeah.
Roughly how far away?
Well, and in here, I will, now this is going to slow things down a little bit because I turned on the geostationaries. But if I pull back far enough, we're going to see, okay, those are GPS satellites. And now we see what's called the Clark ring for Arthur C. Clarke at 22,000 miles out. And you see, here they are out here.
What is that?
That ring is where we put satellites above the equator. At that distance, they orbit the Earth not in an hour and a half, which the satellites closer to Earth are doing, but in 24 hours. And so at that distance, essentially, they stay stationary over that part of the equator. So that's a geosynchronous ring. Yeah.
22,000 miles out?
Yes, the ring. Mm-hmm.
Why are they out so far? I mean, what's the function?
Okay, let me describe if
That's that balance point. That's
Okay.
why it keeps them there.
If I come in a little closer for the moment, I'm going to turn the communication satellites off just for, or actually, I'll turn off the geostationaries, and they, okay, now it'll refresh a little faster. Okay, and the ones that are labeled up here, I'm flying past some intermediaries that are the GPS satellites. Okay.
The GPS have have motors or something, or what that keeps them going?
No, well, they all use solar power, but okay.
How do they keep them from colliding?
All right. The closer you are to Earth, the faster you're going to go around the Earth. So when you're in this close, just a few hundred kilometers off the Earth, you go around in 90 minutes. So an hour and a half, you've done one orbit.
How do they keep them from colliding?
Well, the distance between, because they are so small, we have a lot, but the probability of hit is very low. However, it was just last year that the first two satellites actually collided. And so this is astonishing as it may seem, but they did collide. And it was the first ever occurrence of that. The Chinese also blew up a satellite a few years ago to kind of show that they could, and they created a debris cloud of, actually moved out into a ring of debris, and the space station actually had to be moved a little bit, nudged, so it wasn't going to be under threat of that cloud.
Will that debris eventually fall into the planet?
Yes, anything in low Earth orbit here, that the atmosphere that we see that I talked about being so thin, that's what the visible atmosphere is, actually very thin. So, for example, let me come down over the Alps for a second, just to illustrate. Okay, I'm getting satellites. If I come in really close, they're going to show up like this. But I just want to come down really fast here to give you a sense of the atmosphere. Okay, and actually I'm going to go a little farther because I have time moving so fast that the sun's setting. But okay, if I can tip it over fast enough. Oh, come on! Everything's going so fast. Okay, if I come down close enough, we begin to see the thickness of the atmosphere. Yeah, but the sun is setting already, so we can actually dip into the atmosphere. But I'm sorry because here, let me roll this around. But the farther out you go away from the Earth, the slower a satellite orbits. And you can think about that in terms of the Moon. The Moon takes 1 month to go around the Earth, 1 month. And so...
when you say slower, you mean the speed is actually slower, or just...
Speed is slower. The velocity is slower.
So it's both the speed and the distance that takes up the time?
It's the closer you are to the gravity source, the faster you're going to move.
Kepler worked that.
It has to move faster.
Kepler worked that out as a law of planetary motion. That's right.
How many satellites do we have?
We have thousands.
Thousands.
Yeah. So what
In the clock ring, there's just the one satellite?
Yeah, let me try to actually emphasize the geostationary, or the communication satellites. Let me bring up their properties for a second. Let me make sure that they have trails. And do I see them? Not seeing the trails. Let me go to orbit. Okay, there. So that's the orbit of them right there. And so it's at this distance, which is about 22,000 miles. That the Earth itself is 8,000 miles in diameter. So its circumference around is 12,000 miles. And so...
Is it 25,000 around the Earth?
It's,
Yeah, roughly.
yes, I'm
The
sorry.
equator, yeah.
Yes. Around the equator.
12 to 7.
Mm-hmm. So essentially, the distance from here on out is about the circumference of Earth. And Arthur C. Clarke noted in 1945 in an article that he wrote that if you put satellites out there, you could use them for communication purposes. Yeah. Okay, so what I'd like to do now is I'm going to stop the time, and I'm just going to bring up lunar orbit. Okay, and I want to show, in fact, let me just turn off Okay, all right, I'm going to leave that on, and now we see lunar orbit. And so out at the distance of the moon being here, that it takes 1 month for the moon to go one circuit all the way around. It takes a satellite here 24 hours to go one circuit around. And it takes satellites that are in close to the Earth in here an hour and a half to go around. So now what I'd like to do is turn off the satellites so that everything will go a lot faster here. Okay.
Do they have any elliptical orbits for some satellites?
Yes, in fact, the Molniya orbits, I'll show you those. That these were invoked. Okay, you can hardly see them up here, but those are highly elliptical. Let me change their color. Okay, now we see them. Now these were actually developed by the Soviets because you go faster when you're closer to the source of the gravity. Again, Kepler, and then slower as you're up here. So they go arching up like this, and while they're up here, you communicate with them, use them to bounce off. But because Russia was mainly higher latitude, they needed to have something like this. It was harder for them to launch into a geosynchronous orbit. Yeah, and it was easier for us because we had Florida at lower latitudes, but they had Kazakhstan. And so that's why these highly elliptical Molniya orbits were developed by the Russians. And you can see this is Australia, so this is Antarctica. And so they come very low over Antarctica, but they spend a lot of time up over the high latitudes of Siberia.
They must come with and by Antarctica.
Apparently they do. So in any event, I'll turn off all these satellites now for us. Just a second. I'm toggling them just so that I make sure that we're all off. Okay, there's still a few on. I'm not quite sure which ones or why, but we'll ignore them. Okay, and now let's pull back. I want to show you a little bit of the moon. Okay. And I'm sorry that I still have this up. I want to collect moon. We're good for that. Okay. But okay, so here's the moon. The moon, pull it back just a little bit. Okay, so the moon is actually quite far away from the Earth. It's 250,000 miles. And of course, when the astronauts were there, they came in quite close and orbited, and they saw Earth rise, similar to as they're showing there. But what I'd like to do is actually, we'll center us on the moon. And I'd like to show you the Apollo 15 landing site. Thanks to data visualization that was only recently accomplished in the last 2 years, thanks to some funding from Google. All right, here we go. Bring up, where's my clock? There we go. And it was data that was collected during the Apollo missions. Here, I'm going to swing the moon around to daylight and move us back around. Okay, there we go. So this is a side of the moon, the man in the moon that we see. And Apollo 15 landed right here. And so I'm going to now add in this moon layer. There it is. And so as they orbited the moon, now I'll get rid of all the heads up. Okay, so as they orbited the moon, they looked side to side. They took these individual sort of pieces, these rectangles, like this. So as they orbited in this direction like this, they looked from side to side and got like this picture, then got this picture, then got this picture. But they also got stereo coverage as they did this, which allowed them to come in, and the stereo coverage gave them the ability to get the height. This is Hadley Rill, which is a collapsed lava tube. And now you're seeing the mountains of the moon. And this is effectively the view that the astronauts had flying in over the Apennine Mountains on their way to land at Hadley-Rill.
What's that gouged out? That's not a river.
No, it's actually a lava tube. So lava had flowed, and then it collapsed. And so that the notion is that there are possibly lava tubes that are still that still have their that have not collapsed, and that we might be able to in the future perhaps put a lunar base in a lava tube. That was one idea. But the Apollo 15 astronauts landed right here. But as we fly past, I'll just look around. That's St. George crater. They drove the rover over to. I don't know. You'd have to ask the guys about that. That's Hadley Mountain. That's 18,000 feet tall as some of the tallest mountains in central Mexico. But this gives you a good idea of what the moon actually really looked like. And there is no atmosphere.
Right. So everything on the surface, the dust, everything, it's been that way for millions of years, right?
Billions.
It's not been disturbed though.
It's occasionally disturbed by a very violent impact. And because there's no atmosphere to burn up the infalling stuff, that you get a hard hit. But this is effectively, we are recreating essentially the experience of what it must be like to fly over the moon. And now, this data was captured photographically 40 years ago, but it wasn't until it was digitized by modern means and compared to create the three-dimensional structure that you're seeing here, the underlying height map, if you will, to give you the overall experience of flying over the moon in this three-dimensional sort of landing strip of Apollo.
It's pretty seamless from picture to picture.
It is pretty nice. There's a beautiful crater that comes up if I just allow myself to fly a little farther, and it really gives an amazing sense of what it must have been like to have been there. Here it is. Forgive me, I forget exactly the name of this crater. But here, I'll come down into it. But again, the astronauts were flying about this height off the moon.
Weren't they in a set orbit? They didn't have a chance to.
Correct. They're in a very precise orbit, so that they would hit their landing site. And then these images were captured by essentially the astronaut who had to remain in orbit waiting for the moonwalkers. Al Warden. No, this is Al Warden on Apollo 15, who was responsible for the mapping camera. Buzz was one of the moonwalkers on 11. I know him pretty well. I worked with him as his illustrator for 10 years. So that's the moon, and yeah.
Carter, if I may?
Yes, please.
We're coming up to the end of the tape. Did you sort of get something where we could make a break for about 30 seconds?
Oh, sure. In fact, what I'll do, Harold, thank you, is I'll pull back. That's the moon around the Earth, and I'll also show the magnetosphere of Earth, and I think maybe that's where we can do a transition.
Okay.
So.
We got 2 minutes.
Great. I just.
Is the bathroom break?
No bathroom.
No bathroom?
No bathroom.
And so that's okay. And I'll resettle on the Earth as my target.
What is that then?
That's the magnetosphere, and this is the result of a model constrained by actual observations from a team at Boston University for a solar storm event that happened in 2003. And it shows the structure of the last closed field lines of of the magnetosphere being pushed on by the solar wind. That's just dragged out into a tail away from the sun. The solar wind is the streaming of particles coming out from the sun that are modified by the sun's magnetosphere. Interacts with our magnetosphere. So, but this is the shape that it presents. Yes, it does. At the north and south poles. Just about to say that. Thank you.
Okay, is this the part where we could just stop for 30 seconds?
Absolutely.
Okay, I'm just going to change it.
That magnetosphere,
You can
pulls
talk.
back as a response to.
Yes, it's in fact caught in the flow. In fact, it's reacting to the magnetosphere of the sun as well, and then you have this flow of the particles, which are also sort of caught in that flow. But it's this interaction really between the Earth's magnetic field and the sun's magnetic field.
When you say the satellites, the transmissions are solar powered, but how do they have enough fuel to stay corrected in orbit, or they're using ion rockets?
Oh, well, I'm not sure if any of them use ion rockets. Well, maybe some do. I'm not certain. I'm no expert on that. But there are many exhausted satellites up there. That yeah, so there's a lot of space.